everyone. I'm Melainia. I work at the Stowers Institute in Kansas City, Missouri, and I work in the electron and light microscopy team, so sort of like a core facility. Today I'm going to talk to you about targeting mystery cells in the zebrafish neuromast with correlative serial blockface SEM. So firstly, zebrafish. We work on 5-day-old zebrafish for this project, and the neuromasts are part of a system called the lateral line, which is along the outside of the body of the fish that detects water movement. So let me find my pointer, sorry. So here is this cross-section through a neuromast, and you can see in the middle these cells called hair cells that have cilia that detect water movement. Generally, the lateral line is used to study development and regeneration, has some parallels with our ear ciliated cells, but we're not going to talk about those today. We're going to talk about a slight mystery. So here at the bottom left, you can see a more close-up view of some neuromasts. We have some labeling of the neuromast-specific nuclei in magenta, and then the cells of interest that we're looking for are in green here. And then we can take a closer look at one of these neuromasts here in this confocal imaging stack. So we can see the cells of interest here are now in white and the nuclei are in magenta. And just to make this a bit easier, we have a, sorry, there's something in my way there. Okay, we have a maximum intensity projection here. So the interesting thing about these white cells is that they are not labeled with any neuromast markers at all. So the researchers didn't know much at all about them. And then to add an extra level of mystery, there was evidence of a second nuclei next to these cells, which weren't labeled by any markers except for just a general nuclear stain. So in order to get to a closer look at these cells, see what might be happening next to these cells, we decided we would do serial blockface SEM so that we could easily get the whole neuromast. So this is our system here on the left. It's a Zeiss Merlin with 3View, 2XP. And then just in case you are unfamiliar with serial blockface SEM, I have this little video from Gatan. So you have your sample and your knife inside the chamber of the SEM, and you scan your blockface surface, and then the knife will come in and slice, and you will repeat this for however long of the volume that you need. So this is the technique we're going for. For this technique, since it's a little different from traditional TEM, since you can't post stains sections that you cut like you can in TEM, you have to put all your stain in before you embed. That generally looks like osmium layered with some kind of chemical like thiocarbohydrazide that amplifies the osmium signal, and then an en-bloc staining with UA, uranyl acetate, and then usually a lead staining step. And we've got this specific protocol from this paper here at the bottom. And we also tried minimal resin embedding for this project, which looks a little like this. So in minimal resin embedding, you just remove all the empty resin from around the sample before you polymerize. So we can see our little fish here all filled with metal and infiltrated with resin. You can see the surface details very well, and since the neuromasts are visible on the surface, we hope this would help us to target our area of interest more easily. Next step we would do is put that on a pin that's compatible with the 3V system. So here we have a sample holder, and then the pin would be here, and then you would use conductive epoxy to glue your sample, in this case the fish head, onto the pin. And now we can put this in an SEM before even any cutting, and just kind of get an idea of where we are and what we're looking for. So now we have our picture of our fish head, and we can start to identify some markers here. These 3 neuromasts are the ones that I could still see after I did the mounting, that weren't accidentally covered by the conductive epoxy, which is a bit tricky. But this is enough to overlay our light microscopy for this fish and get an idea of where we want to target first. Since this neuromast here is right next to the eye, it's the first one to come up, it's the obvious target. Plus it has 3 of the cells of interest, which none of these neuromasts are guaranteed to have the cells of interest. Some have 1, some have 2. This one happens to have 3, which is a benefit. So we're gonna target that. And first thing we do before we load it into the 3-view system is to cut away all of the parts that we don't need in an ultramicrotome, as close as I could feel comfortable, to see this is the end of the eye, and the ioneuromast here in the circle should be about there. So we are ready now to load this into the 3-view. This is the 3-view stage. Here you're looking top down if you have the microscope door open. At the top here is the sample holder, and then the sample is clamped in here. The knife is held by this arm. The part of the knife that cuts is in this little oval. So this whole arm will move forward over the sample, pull back to do the cutting, and then retract out of the way for each image. And then this little tube here is a focal charge compensator. Because our SEM doesn't have variable pressure mode, we have to do all our imaging in high vacuum. So this tube will deliver a nitrogen gas to the surface of the block face to mitigate any charging. And so that has to be placed as precisely as possible, aimed at your area of interest, and close enough, but not too close. I usually aim for around 200 microns away. And then if you have a look in the SEM, this is a representation of what you'd see. Your sample here. This is our sample with our eye almost gone. You can see the brain and the mouth here. And all of this is conductive epoxy. And then the focal charge tube here right next to the sample. So we have our acquired image stack of this neuromast. I will just play that through. We acquired at 2 kV, 80 nanometer sections, 100 nanometer XY pixels, and 4 microsecond dwell time, just a little bit of nitrogen. And as you look at the video, you can see that there was some cutting artifacts here due to the minimal resin technique, which doesn't translate maybe quite as well to cutting as it does to, say, a FibSem approach. But we still have enough information here to get started on targeting our cells of interest. And to do that, I will load this data set into a 3D modeling program. In this case, it's 3D Mod in the iMod package. And I will trace each nuclei every 5 to 10 sections just to get a rough idea, because I'm going to use the nuclei that were labeled in the light microscopy data with the neuromast specific nuclear marker as fiducials to more precisely know for sure that I'm targeting the right cells of interest. And so once I've done that, here are all of those kind of stacked on top of each other in 3D space. And then we can ask the program to put a mesh onto that to make it look more solid. And now when we rotate that data, we can see that it matches pretty well with the nuclei of the neuromast. So I'm now pretty confident that we're in the right neuromast for the light microscopy data. And we can target these spaces here in the model that should have these cells of interest. And to do that, I can bring up my Z slices of my image stack and scroll through them until I hit a space where there should be a cell of interest. I can rotate that to be in the right plane of view. And then I can kind of slice away some of the model and say, okay, here is what is in this space. So now we have targeted this space. We have 2 cells that are not included in the neuromast marker specific staining. Now, I would generally just do some tracing, scroll up and down, see which one of these best matches the white cell. And I find out that that is this bottom cell. So I can do that for all 3 of these areas. And now we're getting really close to what light microscopy data has. We have the 3 labeled cells of interest, and what looks like the nuclei of the neuromast. But we do have this extra mystery cell. Is there a second cell next to this white cell? And we did see in our volume data that there is a second cell there. So we can go through and trace that one now. And then it happens that all 3 of these cells do have this second cell closely associated with it. So we've learned a bit now about these mystery cells. And so the researcher had mentioned to me that there were some characteristics of these cells that led her to believe that these could be ionocytes. So namely, access to the surface of the neuromast, this cup-like appearance at the tip, and the close association of 2 cells with like kind of an opening to the outside. And she mentioned that it would be very nice if we could see in the model, the 3D model, evidence of the presence of villi. And so when we look at that model, we see that it's not terribly convincing that there's a villi there. So with this data set, the fact that it maybe didn't have quite enough metal stain, and also the cutting artifacts I would get when I would try to cut thinner sections or put more dose to get better signal to noise, meant that it was a tougher data set to trace. Wasn't terribly accurate. It was hard to tell sometimes where the membranes were. So separately from this, I was working on a protocol for a different project. This staining protocol has a lot more and longer staining steps. It has more high temperature staining steps. So we were about to run a test of this protocol with one parameter changed, and we decided we had room and we would throw in some fish just to see if this would give us a better result. And indeed, it did give us a better result. So this fish is not correlative. I don't have light microscopy data for this fish, but after my experience with the other data set, I felt confident that if there was the cell present in the neuromast, the cell pair present, I would be able to tell and see it there. So I took 3 neuromast ROIs, and 2 out of the 3 had the cell of interest. So we'll play this first one here. I only got a partial, but I did get the cup, the tip area with the cup that the researcher was interested in. And then the second one, I did get the whole neuromast. So the increase in conductivity and contrast, the increased stability, since there was resin surrounding the sample, did allow me to cut thinner sections at 50 instead of 80 nanometers. And I got a lot better signal to noise. This neuromast did take 3 days to acquire, but I think that the results made that well worth it. So if you can see the comparison here between the protocol 1 and protocol 2. Protocol 2 has a level of clarity and contrast in the membranes that allowed me to use some of the semi-automated tracing tools in the 3D modeling software, which made the tracing more accurate and a lot faster and a lot more pleasant to do. So if I then take this partial and I model out this cup area, we can see that this is a much more convincing representation of Vilayet's area. So this is good. And then for the whole neuromast, I was able to model the whole cell pair. And I took the opportunity to give a slightly different viewpoint. So this is arbitrarily rotated and sliced in iMod to give you a view of basically looking from the top down onto the neuromast. So this would be the middle area where there would be the hair cells surrounded by supporting cells. And then outside of that would be the skin of the fish neuromast. And then you can see this here is our cell pair of interest with the little hole or the little opening there in the middle. And so we have our 3D model of our cell pair here. which nicely illustrates the close association. And then definitely, again, more convincing villi here in this model. So basically, both of these protocols were what I would consider successful, but the second protocol allowed a better, more precise, more high resolution data and more clear data. And in my opinion, the biggest reason for that is the more staining, which doesn't always happen that way. Sometimes when you put more staining into a sample, it just all gets uniformly darker. And even though you have more conductivity, you can't necessarily still see the cell membranes very well to do the modeling. It did help that it was embedded in a block, at least to not get, the chipping artifacts. There was some chatter artifacts in the other data set too, the other sample processing protocol anyway. And then did automation with continuous agitation have an influence? It was a big difference between the two protocols. I can't say whether it did or not, but it's definitely something to keep in mind. So with that, I just want to thank everyone who was involved in the project. Julia was the researcher who was driving the project and took all the beautiful light microscopy images. Xia and Morgan were instrumental in helping with sample prep, and Steph helped me to develop the staining protocol in the second protocol. And then just if you're interested, this is the paper where this data is published. And then with that, I'm happy to take anyone's questions. Okay, I'm going to stop sharing just because I can't see any of you. But I can share again.
If you're not a panelist and you want to ask a question, go ahead and raise your hand and I will allow you to speak.
Yeah, please raise your hand if you have any questions. I have a question, Melainia. So do you think the minimal resin embedding, is it worse even your compromise with the sectioning qualities? It really helped with it helped you to locate the area of interest. But could you try to re-embed it something?
I have tried to re-embed, and I still got chatter artifacts. It was on a different sample type, but yes, I did have a minimal resin piece that I put back into resin and embedded again and polymerized again, and it still didn't have great cutting properties compared to just embedding in resin. With this, in retrospect, with this project, I probably could have been like, okay, I want the IO neuromast. It's right below the eye. I'll cut almost to the end of the eye. But it really helped me, as I'm learning to do this, and I'm learning the 3-view still back. This was in 2019, forever ago. So yeah, I think if you need that surface detail, it's really nice to have. But if you don't, maybe skip the minimal resin. And also, if you don't need, say, oh, I need to precisely, have 50 nanometer sections or trace. And it also depends on the sample, because different samples will need vastly different amounts of metal stain. So if you can get that good signal to noise and you don't get the cutting artifacts, yeah, it's all over the place. In my experience, different samples needing different treatment.
All right, do we have any other questions? Otherwise, I can ask some more. Melainia, I actually don't have a serial block phase ACM, but you mentioned about you don't have a variable pressure function in your serial block phase, but you have a 20% nitrogen. You use that to mitigate the
Right.
charging. Is that a common practice, or is that something that you installed afterwards, after you find out you have the charging problem with the instrument?
Something, well, the timing of it was that we bought the instrument and then Zeiss came out with the focal charge system after we already had the system. And once, I mean, charging is, I feel like it's always a struggle. I've never used variable pressure, but I feel like it's probably still a struggle just a little to get that balance between the noisiness that you get trying to mitigate the charge and, you know, the clarity that you get, but too much charging. Once we saw that there was a focal charge compensator available, we just knew we wanted it just to make our lives easier, to have more tools, to have more options. I mostly run it, even if it's 10%, it will get, I don't always need it. Say, if I have a sample that does really well and maybe I only need 10% just to get rid of the charging that's on the very slim edge of empty resin. I frequently have to keep empty resin around my samples because people want the edge of their sample and I can't cut it off. So, you know, even for that, it's good.
Okay, thank you. Kedar, go ahead. You have a question?
Hey, Melania,
Oh,
great work. This is really, really nice work. I just have a question with regards to how much you can squeeze out of your system. So let's just say you have this, you know, you've settled on this magic protocol, and let's say, for example, you've got a zebrafish sample, right? What is your best possible XYZ resolution that you're able to get now? You know, of course, the point being that you know, allowing for the signal to noise ratio that allows you to easily identify and reconstruct small features such as these villi that you're looking at.
yeah, it's interesting. I'll preface the answer by saying that I don't get a lot of pressure to do the highest XY resolution and even the Z resolution for the kinds of things that I usually do. Most people want to maximize their field of view and the amount of volume, which is one of the reasons why we went with serial block face instead of a FibSim. But that said, the best result that I've gotten on resolution is 20 nanometer voxels, so 20 nanometer sections. And that was on high pressure frozen free substituted sample, which I feel like more often gives you higher contrast instead of just dark staining, but I haven't done a lot of free substitution volume work. I think the smallest XY I've acquired was 6 nanometer. That was a really nice signal to noise.
So would you say your, you know, comfort zone would, so if I were to sort of add a part B to the question, you know, 20 nanometers is your best case in Z and say 6 nanometers in XY, but that's your best case, perhaps a little inconsistent or pushing the envelope. What would be your happy zone where you can just be like, hey, I'm going to close my eyes, hit go, and I know that I will get a really good volume?
I've tended to default on that around 15 nanometer XY and 60 nanometer Z because it's comfortable and because it bends well, it bends nicely, right? So you bend the 15 nanometer XY, you get to 60. It's a nice,
Great.
you know,
Yeah.
clean thing.
Appreciate it. Yeah. Great work. Great work.
Thanks.